Hello and welcome. Now we come to topic 4, which is on the asymptotic unknown input observers for time delay systems. I'm very excited to say that we're going to have a series of presentations for topic 4. Um, so the objective is to design unknown input observers to asymptotically estimate unknown inputs of a wide range of time delay systems. So we have a series of presentations. We're going to look at a wide range of time delay systems, and then we're going to estimate asymptotically the unknown inputs. The key features of this topic is that we're going to introduce the new concept of generalized functionals. This is will be a bit clear later on. And so we got a definition of a generalized functional, and we're going to design novel, new, generalized functional observers for time delay systems. What happened in here is just the key features, just like in our previous topics. The way we do the decomposition is that the targeted unknown input contains the least number of output differentiators. And the thing about this decomposition for time delay systems is that we're going to get a generalized functional, no longer just a functional, but a generalized functional. And that functional actually contains multiple stack delay terms. And so the most effective way to estimate the unknown input is to directly estimate the generalized functional using generalized functional observer. So we got generalized functionals, and we don't just design a stack observer and then realize the generalized functional, the estimation of the generalized functional. Instead, we design a generalized functional observer directly to estimate the generalized functional. This is the most effective way that will give us the least, the simplest structure for the unknown input. Okay. So we're going to have a series of presentation for topic 4, and we just like to concentrate on demonstrating that when we are dealing with time delay systems, the decomposition of the unknown input uh, when we express the unknown input in its own entirety, we can do that, and it will be a linear combination of the output measurements, a linear combination of the first derivative of the output. We want it to be the least number of output derivatives, and then it's going to be a generalized functional. So we're going to show that will come that will arise in our decomposition technique, and then that will give us a whole heap of series of presentations where we will explore, where we will discuss the advantages of estimating generalized functional observers. Why is it better to estimate generalized functional observer instead of just the standard functional observer or the stack observer? And we will show that we can actually relax the conditions when we design generalized functional observers. So that will be very intriguing, and that will be extensively covered in topic 5. So topic 4, what we're going to do is we're going to show that when we decompose the unknown input for a wide range of time delay systems, we inevitably will results in generalized functionals. And the need for estimate those generalized functionals directly is based on the design of generalized functionals. Okay, so let us concentrate on part one, where we just consider a simple time delay system with a constant time delay. So we have this extra term in here, that is the delay term in the stack. And we got, for the sake of simplicity in the presentation, we just consider a single unknown input. And we have stack vector of dimension n, output measurement vector of dimension p, an unknown input, and the matrix C is in canonical form, which we can always transform the system into canonical form. And what happened in here is we got tau here is a positive scalar, and it's a known time delay. So this is a classic, very simple classic time delay system, or a system with a constant time delay. And we also have a continuous initial function. That is a continuous function over the time interval from minus tau to 0. So we like to estimate asymptotically the unknown input when time goes to infinity. So this is just like in our previous topic, where now we have this extra term in there. So this is a time delay system with an unknown, with a time delay system with a known time delay, constant known time delay. So the thing here is we will show that based on our metric decomposition technique, we can express the unknown input in this form, which is the simplest form. Again, it contains the first derivative of only one output measurement, and we call it yi of t. Of course, if yi of t, the first derivative is used, it has to satisfy the matching condition, which is ci times d must be non-zero, and that non-zero equal alpha I, and then beta I is 1 over alpha I. So what happened in this decomposition is that we got the first derivative of the output measurement yi of t. And as usual, this came from the previous topic. Here we got an extra delay output measurement yi of t. And a linear combination, we will show it later on, it's z of t. So it's just in the form similar to the previous discussions. We have an extra delay output measurement and a linear functional z of t. Now, what is it? It is actually a sum of the linear combination of the stack vector x bar 1 of t and the delay of it. So when we look at this function now, it's no longer just a single term. It has another term here. And this functional is what we call, what we call it in this book is called an generalized functional, a generalized functional. And so if we have this generalized functional, which is a combination of the instantaneous linear combination of the instantaneous stack vector and the delay stack vector, then the question is when we want to estimate this unknown input, what would be the best way to go about doing it? Do we just do it like the hard way, or the easiest way, the straightforward way is to estimate the entire stack vector and then delay it and then realize the estimation of this function by that way, or do we do it directly? And so if you look at the book that we actually investigated in chapter 4, we actually did an exploratory shot for it. We actually explore what are the possible options that can give us the least simplified, the most simplified structure for the estimation of z of t. And then we come to the conclusion after extensive investigation, which is part of the third part of the book, which we show that, well, the best way to estimate in one go. Now, we talk a bit about this a bit later on, but to continue on, when we do the decomposition, we obtain this unknown input expressed in this simplified form, which has the derivative of one output measurement and a generalized functional, which is expressed in this form. And we also obtain a reduced order time delay system as well. So this reduced order time delay system itself is disturbance free. Just like in our previous topic 2, when we have a single unknown input, and when we express the unknown input in its entirety, we also obtain a disturbance-free reduced order system. Here in this situation for time delay system, we also get a reduced order, disturbance-free, but with time delay in there. So we call that this is a reduced order time delay system, which is disturbance-free. All right, so that's what we're going to show. We say that, okay, when we look at time delay system with a constant time delay, and if we apply matrix decomposition technique, which is decomposing the unknown input in its entirety, we get equation 1, which is the unknown input itself. We have the linear combination of the stack vector and its delay stack vector. We call it a generalized functional, and we obtain a reduced order disturbance-free time delay system. So that is what explained in here. Equation 1, we just have one output differentiator, which is this one here. And in equation 2, this is the exciting bit about it. In equation 2, if we just simply call minus a bar 21 and minus a bar d21 as f and fd respectively, so we can see that this generalized functional itself is the sum of the instantaneous linear combination of the internal stack vector and linear combination of the delay stack vector. By the way, this is x 1 bar 1 in here. Okay, so it's a generalized functional, and the system itself here is a reduced order time delay disturbance-free system. And of course, as you can see, that the estimation can be done if we can estimate this generalized functional. And if we can estimate this generalized functional such that time goes to infinity, it's asymptotically approaching the true functional, then we can guarantee that the estimated unknown input asymptotically converges to the true unknown input as time goes to infinity. So it boiled down to, what is the best way to do it? What is the best way to do it? And as we discussed extensively in chapter 4 of our book, we look at various options. But then we actually can conclude that the best way to estimate this generalized function is to do it directly, not through estimating this, or not by estimating this functional itself and then another functional itself and then delay or whatever there. No, that's not the way to go. So that comes to the very important contribution of our new book, which is on the systematic design of generalized functional observers for time delay systems. And so let us show that we can actually achieve the following decomposition. Okay. And then we will talk about the significance of generalized functional and so on later on. Right, so the decomposition itself is really straightforward, by the way. When we look at, let's say we pick the first output measurement, and we want to express the unknown input in terms of the first derivative of this measurement, then we require C1 times D, which is alpha 1, which is non-zero. And also for the sake of simplicity, we assume that matrix C is in the canonical form. So that it's straightforward. We can then pick the invertible metric V. And the thing here, we select the metric P in this structure so that we can have the most simplified structure for the row matrix V1, which is only one non-zero element in there. And therefore, we will pick the first derivative of output Y1 of T. And similarly, when we choose the transformation metric T, where E is in this form, then, by the way, if T is in this form, we always get it in this structure. And then this metric E is chosen in this particular form so that we can have V1 times C times E is a zero matrix. So this is just a standard way of doing the decomposition based on our previous discussion for topic 2 and topic 3. So we then define a new metric with the A bar, and we partition accordingly. Now we have a new A bar D matrix which came from this delay term in the model of the system. So when we apply the transformation x of t equal to t, capital T times x bar of t, then we have a new A bar D matrix. And that A bar D matrix is given by this expression. And we also partition that metric into submatrices accordingly, just like the dimension is similar to the dimension of those submatrices in A bar. Okay, so we specify the dimension of all these submatrices. And then we also partition the vector x bar of t in terms of x bar 1 of t, which has dimension n minus 1. And this is of dimension 1. So when we apply the stack transformation into the original time delay system, we can rearrange and we can split that into two equations. The first equation is this equation here, and the second equation is this equation here, which explicitly can give us the expression for the unknown input d of t. And just like previously, we also consider output measurement vector. And then we multiply both sides by metric V1, V2, which is the inverse of that. So we got the first equation, which is exactly what we got from topic 2, because we import this structure. And because of the identity matrix, we have all these identities expressions here. So we have the x bar 2 expressed in terms of yt, which is basically y1 of t. And then the other reduced output measurement is given by this. So by substituting x bar 2 equal to v1 y of t back into this equation, then we arrive at the following reduced order time delay system. Reduced order time delay system. And when we look at this reduced order time delay system, it's actually disturbance free. And it has the delay stack vector in here. It has the output measurement y1 of t and y1 t minus tau. By the way, the output measurement is available, so we can always realize its delay term, delay output measurement. And the output measurement y bar t is given by that. Then once we substitute this expression back into this equation here, and after some rearranging, we have this equation where the unknown input is explicitly expressed in terms of the first derivative of the output measurement y1 of t. Beta 1 is 1 over alpha 1. Alpha 1 is the product of C1 times D. And so we know alpha 1. It has to be non-zero. And that's why, by the way, to asymptotically estimate the unknown input, it's inevitably we need to use the derivative of first derivative of the output measurement. In this situation, we have the least number of output differentiators. And we also can get gamma 1 in terms of y1 of t. And where that came from? It actually came from here. When we move it to the left-hand side, we got minus I bar 2, and then x bar 2 of t, v1 y of t. v1 y of t, by the way, is 1 over alpha 1 times y1 of t. And that's why we have this expression here. And similarly, we also have a delay measurement of output 1. And the key thing here is this linear functional, which is a generalized functional. All right. So which is a generalized functional. So to be able to realize the unknown input, we basically will design a generalized functional observer to estimate that two terms combination there in one go. And so it's called generalized functional observer. So we design a generalized functional observer for this reduced order time delay system. And to our knowledge, there are so many results in the literature that deal with a linear functional observer for time delay system, or reduced order stack observer for time delay system. But this is the first time. This is the first time that we came across the problem of estimating the generalized functional directly. Okay, so this is, we highlighted in our book, we mentioned that when we actually do the decomposition or the decomposition of the unknown input vector into its entirety, we will come across a generalized functional, whether it's a simple generalized functional like so far we got it in here, where we just basically have this term in there. Now bear in mind that when we have multiple delays, then this generalized functional will be like a sum of multiple stack delay terms. Okay, contain multiple stack delay terms. We could have it just like what we just went through, as a combination of x of t and x minus tau, or we could have more, or we could have combination of two non-commensurate delays and so on. Now, the effective way, an effective way to estimate the unknown input is to estimate the generalized functional directly. Okay, we keep reiterating this message because we will show later on in our expository research later on. We will see that, which is third part of the book. We will demonstrate the effectiveness of estimating the generalized functional directly. Now, one thing we like to mention in here, which is very important, is that in the literature, at the moment, in the literature, there are many results available for designing a stack or functional observer for time delay system. But they are mainly, this is the key, they are mainly deal with the problem of estimating the stack vector or a linear combination of the stack vector. Never there is a need or reported a need or or for estimating the generalized functional directly. Okay. So this is the thing. This is the first time. This is the first time that we show that there is a need for estimating a generalized functional. And this came from the unknown input asymptotic estimation problem. If we did not consider, if we don't consider the asymptotic estimation, if we don't consider the decomposition of the unknown input in its entirety, we will never come across this problem there. We will never come across it. In here, we came across it because that's what it is. This is actually a linear combination of the instantaneous and a linear combination of the delay stack vector. So there is a need for estimating this generalized functional directly. Okay, so that is the thing there. So it's a novel way discovery in this book that that we need to estimate this generalized functional by using generalized functional observers. Now, because in the literature, uh, estimating generalized functional is not considered. It's not being reported. So that's why the significance of estimating a generalized functional was not really realized. So in this book, which is the third part of the book, we will conduct a detailed investigation into this problem, and we can show that generalized functionals observers can bring significant extra degrees of freedom and relax the observer at certain conditions. So we will do that extensively in a whole series of presentations, which form the third part of the book. And naturally, you see that we come across a situation that sometimes when we design an observer for time delay system, we can have using generalized functional observers, we can have a situation where the order of observer is actually higher than the number of the stack variables, and that is just a very intriguing situation. So we will show that if we just do the normal functional observer where we estimate just a linear combination of the instantaneous stack vector, there might be situation where we cannot do it. Even if we go up to an order equal to n, we're still not able to do it. But by introducing a delay functional and the sum of that together with the instantaneous, so in other words, by estimating this function directly, we can actually go to a high order and we can achieve asymptotic estimation. So this is something very intriguing. And we can also demonstrate that estimating the generalized functional directly can also reduce the complexity, the hardware, and practical implementation, and so on. So what happened in here is once we obtain an unknown input, which is expressed in its entirety like that, then the estimation of the unknown input can be realized by design a generalized functional observer. Okay. So at the time being, in this current presentation, we just like to show the decomposition, and then we will leave the topic on design generalized functional observer in the next topic, where we will extensively looking into the theory behind that. And so if we look at the decomposition or the unknown input estimation for time delay system, particularly for this time delay system, we can see that we can adopt the metric decomposition technique, and we can express the unknown input in its entirety. We see this one here, and in this entirety here, it has only one output differentiator. And we also obtain a reduced order time delay system. The key point to the decomposition here is the unknown input is in terms of this generalized functional. And so we will develop theory techniques for estimating this generalized functional directly. And therefore, that will give us the most simplified unknown input structure. Okay, so that basically the introduction to this topic 4, where our focus is on asymptotic unknown input observers for time delay systems. And time delay systems here can be a wide range of time delay systems. We just show the first one, the decomposition for the first simple time delay system, which is this one here. But the key point to this is we come across a new definition, a new term, which we call it generalized functional. And we demonstrate that there is a need for estimate that generalized functional directly. And so that becomes like design a generalized functional observer to estimate this generalized functional for this reduced order time delay system. Okay, and that will be the topic of discussion, extensively discussion later on in topic 5. Okay, so thank you very much for watching. I'd like you to join me for the next presentation. The next presentation will just follow in from the logic of this part, where we going to look at a time delay system which now has a delay term which is CD, XT minus tau in the output measurement vector. So sometimes we can have situation where the output measurement vector is not just an instantaneous of the stack vector, combination of the stack vector instantaneous, but might be a sum of that. So the question there is, how do we do the decomposition? How do we explicitly express the unknown input in its entirety? and what sort of expression, what sort of conditions that we're going to impose, we need to impose on, for example, the matrix CD. Can we use our existing decomposition technique to apply to this system? And if so, what sort of the structure, the form of the unknown input going to look like? Now, just a bit of a head up. What we'll see that the linear functional, generalized functional will no longer just include the term x bar 1 t minus tau. It will also have x bar 1 tau minus 2 tau, for example. And that is something very intriguing. So let's say if I just jump ahead a little bit, just to show you the assignments that we're going to see. So when we look at this kind of system, chapter 5, we're going to see that when we do the decomposition, for instance, for the simple situation constraint, we come across the decomposition where we get a reduced order system. We get a reduced order time delay system, but that reduced order time delay system also have a delay term in it as well. When we look at the decomposition of the unknown input, it's a combination of x bar 1t and x bar t minus tau. Also, as the constraint is relaxed, for example, we will come across a situation where, wow, look at that decomposition. We're going to get a reduced order time delay system with multiple delay terms in there. As well as the unknown input itself is a combination of a generalized functional. This is a generalized functional. And so the key, very important question is how do we design generalized functionals? Generalized functional to estimate generalized functionals. How do we design generalized functional observers to estimate generalized functionals for time delay system with multiple delays? Okay, so this is just a text of what to come in the next series of presentations for topic 4. Okay, and so thank you very much for watching, and I hope you can join me in the next presentation. So thank you very much, and bye for now.